Hello everyone. So today we will be solving concert tickets from CSES. So in this problem we have been given some tickets, like more precisely tickets and their prices, and then we have been given M customers. Now each customer is kind of bidding a price, and uh, and for each customer we have to return the maximum value of a ticket which is smaller than the bidding amount for the customer. So for example, these are the ticket prices in this test case, and if a customer is bidding 4, so we should return the maximum ticket cost which is smaller than 4. So for here 3 is the answer. Similarly for 8, what is the maximum ticket price we can have when 8 is the bidding amount? So here if we look at it, we have two candidates, 7 and 8. 8 being the maximum amount which is not exceeding the bidding price. So for this 8 we will be returning 8. Now 3. Now when 3 is coming up again, so we have already allotted this ticket to the first guy, right? Now it is also mentioned that like uh, each ticket is when like each ticket will be assigned to one guy and we cannot reassign that ticket to some other person. So 3 will be gone here because 3 will be assigned to the first guy. So we will be left with 5, 7 and 5. So if we look for 3, we do not have any ticket that is smaller than 3. So we will be returning -1. So, in this problem, looking at the constraints, like n and m are between 1 to 2 times 10 to the power 5. So, if we think of a brute force approach, so one brute force approach will be like uh, for each bidding amount, okay, we'll be iterating over all the tickets and we will try to find out which ticket is very close to the bidding amount. Now, again, we have to make sure that once we are assigning the ticket to this bidding amount, we have to remove that from our data structure, like whatever data structure we will be using to store these tickets. Now, with that approach, we will be doing a kind of order of n cube operation, or to be more precisely, it will be like m times n times n order of operations, because m being the number of bidding amounts, okay, and n being the number of tickets. uh I can say something like tickets, and this n is for the deletion operation that we will be doing once we have assigned the ticket to one bidding amount. So this will be the time complexity, and looking at the constraint, I guess we will be exceeding the time complexity. Now the optimal approach is to think in the direction of binary search. Now uh, in binary search, what we can do, we can think of finding the lower bound, or upper bound will also do the work. So if you guys are not familiar with what lower bound is, so lower bound basically means like if I have a shorted array, let's say it is 1, 2, 3, 4, 5, 6, okay, and if I ask you like let's say for a given value x equal to 5, okay, so what is the lower bound of 5 in this array? Now lower bound basically tell us which value in the array, let's designate as val, is the maximum value and it is less than my x. So this is lower bound definition, okay. So which is the maximum value in the array which is less than equal to x. Now, if x is already present there, then my lower bound for 5 will be 5. Now, if we think of a scenario, if we have been given this kind of array, then lower bound will be 4, because this is the maximum value which is less than x. So this is the definition of lower bound. Another concept we have is the upper bound. Now, upper bound basically tell us like what is the maximum value, or to be more precisely, what is the minimum value, okay, which is uh, greater than my x. Okay. Now, if you think of this, so this also assume like your data structure is shorted. Now, as per this definition, if I ask you like if x equal to 5, what is the upper bound of x? Then it will point to 6. Now let's assume we have 7, 8, 9 on the right. Then it is the minimum value which is like more than x. Now if you look at it, like we do not have that equal to sign here, okay, like as we have in lower bound. So yeah, so in upper bound we are kind of doing a strictly increasing kind of thing. So this is upper bound definition. Now in this problem we can either opt lower bound or upper bound. So if you guys able to understand how lower bound and upper bound works, then let's take this example and let's try to apply this concept here. So we have been given the ticket prices, which is 5, 3, 7, 8, 5. Now if we short this, it will be 3, 5, 5, 7 and 8. Now let's look at the bidding amounts. So first 4 will be given. Now for 4, if we find the upper bound, like the minimum value in this array which is more than 4, then we have two candidates, which is 5 here and 5 here. Now upper bound is something like it will give you the index of the element, like in first index of the element which satisfy this condition. So our upper bound will point to this value, or you can say, let's say this is 0, 1, 2, 3, 4. These are like indices. Okay. Now upper bound will point to first index. Okay. Now by finding this upper bound, I can be sure that whatever values are on the left of this upper bound will be at least 4, right? Because this is the first value which is more than 4. So whatever value comes before this value, that will be at least 4. So I cannot have a value like 4, 5, like something like let's say 6, 5, 5. First of all, this is like not in the short order, so I will not be having 6 here. So let's say we have another 5 here. Now as per upper bound definition, this is also violating, because then our upper bound will be pointing here, not here, right? So yeah, so by upper bound definition, we can be sure that whatever values are on the left of my upper bound, that will be at least the value for which I'm calculating the upper bound, right? So here you can see like if my upper bound is pointing here, then I can return the previous index of that upper bound. So which is 3 here. So for 4 you can see like 3 is the answer. Now let's look at 8 when 8 is asked. And also like we have to remove this element once we have picked it up. Okay, let's say we have removed it. Now we are left with this array. Now when 8 shows up, if we find the upper bound here, now as per definition, upper bound will be giving the first index in the element, which is like the minimum value which is more than my x. So let's look here. So 5, 5, 7, 8. So for 8, none of them are satisfying the upper bound definition. Now, let's say you have a array and on that you are applying this upper bound, then upper bound will be pointing to somewhere at the end pointer. Like in every uh, like linear data structure, we have this end pointer, which basically helps the compiler to know about like what's the size of the data structure. So for example, if we have a list, let's say 1 2 3 4 5, and when we are allocating space for it, or let's say when we are storing this value in the RAM. Okay, now this is a contiguous segment of the RAM, right? Now the RAM has to know like up to what I have to store the value, so it automatically pulls a null pointer here. Okay, now this concept is necessary to understand what will happen with 8. Now for 8 we do not have any value that satisfy upper bound, so upper bound will basically points to like it will point to this null pointer that we have here. Okay, but yeah, so as per our problem, what we are doing is like when we are finding the upper bound, we are looking at the previous index of that upper bound, right? So we will be giving 8 here. Like upper bound is this value, but for our like answering the query, we are doing something like whatever upper bound index we found, we are doing a -1 on that, so that we will look at the previous value. Cool. So 8 will be gone, so like as it will be assigned to the second person. Now 3 will show up. Now in this array, if you look at it, so my upper bound will be this 5 for 3. Okay, like this is the minimum value which is more than 3. Okay, so here if you look at it, we cannot do this operation, right? Because this will be gone and this will be gone. So 5 is at 5 will become my zero index here, like after all this, after this two deletion, right? So 5 will become my zero index. Now when my uh when I'm at the first position, I cannot do this operation, right? Because this will result in -1, and -1 is like we do not have indices in negative numbers, right? So whenever I'm pointing to the start of the element, like if my upper bound is the start of the element, then I'm sure that I do not have any elements on the left of that upper bound, right? Because upper bound is the start of the element. So in this case, we cannot do this operation. So we will be returning -1. Cool. So this is one part of the problem where we can use upper bound and lower bound, and we can figure out like how to answer the query. Now the next problem is what data structure to use. If you go for a simple vector or a array kind of data structure, like let's say you are using CPP, then a simple array and a data structure, like in that you can apply this to operation, lower bound and upper bound. But after the assignment, we have to delete those elements, right? Now deletion in arrays or vectors, okay, it takes linear time complexity. So we will be dealing with n square time complexity, even if we are doing like a upper bound implementation. Now for this problem, we can use something like multiset kind of a data structure. Okay, now multiset is a very powerful data structure. Now it is something based on the concept of set, but it allows us to have duplicate elements. So for example, if I store this in a multiset, it will be stored in a sorted fashion. Okay, and it will ensure that the unique elements if they have duplicate, that will also be there in the data structure, which is very different than a normal set, because in set we only store unique elements. Now for this problem we cannot use a set, because it is possible that maybe two fives will be used for some other queries. Like for this test case, we do not have that, but let's say a test case arrive for which we actually require two fives. Let's say two fives were assignable to some bidding amount. If we go with a normal set, we'll be losing out all the fives that we have. It will only pick one five. But if we go via a multi-set approach, we will be ensuring that we have all the elements and we are storing it in a sorted fashion. Now, another interesting fact about multi-set is that their order of deletion is in log n, which is much better than our linear time complexity that we are getting from vectors and arrays. Now, with this in mind, so we will boil down our time complexity to be like, we will be iterating over all the queries that we have. So we'll be doing m steps, okay, to answer each query. Now, finding the upper bound is a log n operation, okay, like because these two are based on a binary search algorithm, okay. And after this assignment, let's say we got an assignment like we can assign this bidding amount to one ticket, okay. We have to delete it, which is again a log n, which is again in the order of log n. Now here you can see we are doing much better than our previous brute force approach, which was a m times n time complexity. Here we have reduced it to m times log n, which is very fast and it takes less number of steps to reach at the answer. So yeah, so now we can jump down to coding. Cool. Yes. Okay, so let's quickly take the input. So we have been given n and m. Now to create a multi-set, you just need to use this syntax. Let's say I call my multi-set as a finder. Now let's take the ticket prices and I ticket price. Let's take this input. Cool. Now our multi-set is populated with all the ticket prices. I guess I missed this. Okay. Now let's answer all the queries. 0 m I. Okay. Now this will be bidding amount. Okay. Now for this bidding amount, we need to find the upper bound first. So auto IT, or let's say UB pointer. So upper bound returns a pointer to the element. Okay. Now in order to convert it into an index, you have to, so whatever pointer you are getting from upper bound, you have to subtract the like the starting pointer of that data structure, which is like the begin that you have in C++, like the data structure dot begin. Okay. So we can check the starting element with this, or if we simply check whether pointer is equal to ds dot begin, that is also sufficient to check whether we are pointing to the first element. So let's do finder. And yeah, one cool thing about multi-set is that this upper bound and lower bound are like defined methods in that data structure. Just like you have pushback and insert and delete, you have in vectors. So upper bound is already there in the multi-set data structure. So we can directly call it as a method here. And I will be giving the bidding amount here. Okay. Now I will be checking whether upper bound is pointing to the first element. So which is nothing other than finder begin. Okay. Now if my upper bound is pointing to the first element, that means I cannot do this operation, right? Like upper bound minus 1. So I do not have any element before my upper bound index. Okay. So I will be simply printing a minus 1 here. Else I will do a pointer arithmetic, which is like subtracting the pointer, like moving my upper bound pointer to the previous index, and I will be printing that. UB pointer. Since this is a pointer, so in order to print it, I have to dereference it. And then once this is assigned to the bidding amount, I have to delete it. So finder. So to delete it, I have to do erase, and I can pass the pointer here. Cool. Let's run this. Yeah. So we got the answer, and let's quickly submit this. Cool. All got accepted. Now I've already discussed the time complexity. So for this for loop, like when we are computing the time complexity, it is not dependent on this, but but in this case we have to consider this because it is not a normal vector. Okay, it's a multi-set, so it's not like we are pushing in a constant time. So insertion is taking log n, and since we will be doing n times, so this for loop time complexity will be big O of n times log n. Okay, and then we have this thing where for every m we are doing a log of n operation, and if we are finding anything, then we are doing a deletion, which is again a log of n operation, and this we are doing for m times. So big O of m uh, m times log of n times log of n. So yeah, this is the time complexity. Now here so this is the overall time complexity. Now here if you compare based upon n and m, one of the quantity will take the dominance. So if m is higher, then this will be the overall time complexity, but if n is higher, then this will be the overall time complexity. Now because log of n are very small quantities, okay, as compared to n itself, so the overall time complexity will be like a big O of max of this two time complexities. Okay, now let's quickly do the space complexity. So we have a multi-set. Now in that we are simply putting all the ticket prices that we have. Now we have n ticket prices, so it will grow linearly, the our multi-set based upon our input. Then here we are not doing any insertion, or we are not increasing the data structure. Here we are doing a deletion, so this will not take much, like this will not consume any space, only this part will be consuming space. So yeah, so the space complexity will be big O of n. So yeah, these are these time and space complexities, and yeah, so we solve this problem. So I hope you understood the approach and the use of multiset and the upper bound concept here. Now I have used upper bound, so feel free to do the same with lower bound. Lower bound is also there, and you will get the same time complexities. And so yeah, so these are the concept behind this problem. I hope you learned something new, and just stay tuned to watch more videos.